In the last several videos, we've been sort of building up this concept of our energy model and how to apply it to different situations. We're essentially we define some system, and inside that system, we have kinetic energy, potential energy, thermal energy, and those energies can, change form, go back and forth uh, between those types. And inside that system, we have sort of a total energy that's conserved unless there's some forces, external forces applied on that system that do external work that can change the total energy in that system. And we've built up a nice sort of model of how to look at systems from this energy point of view. In the more recent videos, we expanded from a particle model to a rigid body model, and we built off this example of a wheel that, when spinning, clearly has some kinetic energy with it. So this led to our kinetic energy being split up into two types: a translational kinetic energy and a rotational kinetic energy. And we've done a few examples, and we've looked at situations where we can use all of these principles and analyze some situations that, when previously, when we just had sort of Newton's laws and dynamics, would have been much more difficult to sort of sort out. So this was a really useful way of looking at a lot of situations. Um, it it doesn't work for everything, though. I mean, the principles do, but approaching things from an energy point of view aren't always the simplest things to do. And today, what we're going to do is we're going to introduce the concept of momentum and things like that to just sort of add more concepts to our toolkit and how to think about how things work. One situation that is clearly an example of where thinking about it purely from an energy sort of perspective doesn't bear as much fruit as other views, is the idea of collisions. So if you think about a collision, you have two objects, in this case, a tennis racket and a tennis ball, um, and they're both moving and they come together to the same place at the same time. And for a very brief instant in time, interact with each other really quickly and strongly, and then uh, go in opposite directions or deflect off each other. Um, if you think about what happens in here, well, in this case, we have a tennis ball that hits the tennis racket. The strings kind of stretch a bit and deform. The ball flattens a bit. You have this sort of compression. And this all happens really quickly. There are going to be some dissipative forces in that we don't really know the details of, in most cases. So there's a lot of things in our energy model that we just don't know the details of that happen in there. And it can make it really hard to use the energy sort of model we've been using to analyze that. So how can we think about this in another way? And one of the ways we can think about it is just going back to Newton's laws. Everything kind of comes from those things in this class. Um, what we would call this very quick sort of force that let's say the tennis ball sees in that collision is an impulsive force. All right. So we have, if we look up here, we have the ball coming in with some initial velocity. It collides with the racket, experiences a force for a very small delta t, and then afterwards bounces off that racket with some final velocity, right? And if we were to plot that force, and we'll start with one dimension for simplicity, what you see is there's no force when it's just moving with that velocity. It starts to compress when it hits the racket. That force gets much bigger. It fully compresses and then starts to expand back to its normal size and bounce the other way. And that force comes down, and we have this small delta t where the force exists. It's very nonlinear, so or it's not constant rather. So Newton's laws and the way we use them aren't as straightforward either as the energy. So we have to kind of think of a new way to approach this problem. How do we do that? Well, let's start with Newton's laws that we do. So if we're looking at that ball during that collision, right? We know that we have force is equal to mass times acceleration, which is equal to um, mass times the derivative of the velocity with respect to time, right? Now, right here, this is, a sort of differential equation, mass times dv dt. Now, in the things we're going to look at in this course, for the most part, we're going to assume that the mass of that ball doesn't change; it's a constant. So we can actually bring that into our derivative, and this ends up being the time derivative of the mass times the velocity. And when we do that, we can. This is, right here, we can define this mass times velocity as our concept of what we call momentum with the symbol P. This is mass times velocity, and we're going to define momentum to be equal to that quantity. So Newton's second law, just with that substitution, can be written as force is equal to the derivative of the momentum with respect to time, where, again, momentum is mass times velocity. And just to be explicitly clear, because I was sloppy with my notation, these are still vector equations. That momentum is a vector. It has a direction and a magnitude. The direction is the same direction the velocity is in. And if you multiply it by the mass, you get the magnitude. The velocity by the mass, you get the magnitude. So what can we do with this? Looking at this collision, right? Well, we can do the same sort of thing we did at the very start of our energy discussion and do a bit of calculus on it. And if we separate variables and bring the time over to the one side, leave the momentum variables on the other, and integrate over that collision, from the start to the end and the time it started at to the final time of that collision, we can integrate this. And the momentum, this integral is easy. Integrate one with respect to any variable. And this ends up being, after you put in the limits, the final momentum minus the initial momentum, or just simply the change in momentum of that ball or whatever object we're analyzing. And this over here looks pretty similar to how we defined work, where we integrated a force. But when we were looking at work, we integrated that force over the change in position. Remember, work was the force times the displacement. In this case, it's over time. We define that to be what's called the impulse. And we use the variable j for that. So the impulse is sort of the integral of the force applied over a given time. And what it does is that causes a change in momentum of the object. And, knowing our calculus, this integral is just the area under the curve here. So if we want to look at, what's the change in momentum of this tennis ball after it gets hit by the racket, we can just integrate the force that it experiences over that really small time, and we get the change in momentum, which relates to final and initial momentums or velocities. Um, so that's what we end up. We've defined a few things here. We've defined our momentum to be just the mass times the velocity of the object we're looking at, and we've defined the impulse down here to be the integral of that force over the time it's applied for. And again, these are vectors, so we can look at it in terms of components. And graphically, it's just the area under the curve. Now, again, this is useful. It's a nice way to think about things, but it can be kind of actually, it doesn't, in my mind, give us too much more to work with yet, right? We still have a pretty complicated force as a function of time. We would need to know that to do this integral. So, useful, but not extremely much better, any better than our other methods so far. But it comes in really handy if we just do a few more things with it. So where it really comes in handy is if we think about both objects in that collision. So moving away from the tennis ball, tennis racket thing, let's just think of just two general objects, one and two balls, say, that are moving towards each other. They collide, have that force on each other, and bounce off afterwards. Now, if we look at the forces applied on this, we have, ball one experience a force from ball two acting on it And from Newton's third law, we know that force is equal and opposite to the force ball 2 feels from ball 1 acting on it. So the forces involved in this collision are made up from those action-reaction pairs, those equal and opposite forces, right? So knowing that, Newton's third law makes this idea of impulse and change in momentum really useful, right? If we look at, so let's use those concepts to analyze each of the two balls, right? So if we look at ball 1, right? We just did this. We know F net on ball 1 is equal to the change in the momentum of ball 1 times dt. We do that separation of variables thing where T1 to T2, sorry, T2 of that force, dt, which is the impulse, is equal to the change in momentum of ball 1, right? And we know that this force is force of 2 on ball 1, right? So we know that we have an equation that tells us how much ball 1 changes its momentum. Now, if we come over here and look at ball 2, we can do the same thing. The net force on ball 2 is equal to dp2 times dt. We can do the same sort of thing, find out what the impulse is, and determine what the change in momentum of ball 2 is, where the force acting on it is the force of 1 acting on 2. And here is where Newton's third law comes in handy. We know that the force of 2 acting on 1 is equal to negative the force of 1 acting on 2. So if we use Newton's second law here and make one of these substitutions, we know that this is negative this. Or what that amounts to is telling us that the change in momentum of ball 1 is going to be equal to negative the change in momentum of ball 2. And this is extremely useful to us. This is telling us that P1 final minus P1 initial is equal to negative P2 final minus P2 initial, or P1 final plus P2 final, just bring this negative over to the other side, is equal to P2 initial plus P1 initial, right? Which is the total momentum at the start, or final, in the way I've written it, is equal to the total momentum at the end, right? These are equal. So if we look at, at the start, there's some P1 initial and some P2 initial. If we take P total and just define the total momentum of that system as P1 plus P2, what we get is that it's conserved, right? So what that tells us, and we haven't, we haven't used any assumptions about the forces or anything. They can be weird, non-constant, very quickly changing. No assumptions have gone into that forces. So we've been extremely general in this case. And what we've sort of shown is that that total momentum of the system, if all the forces involved in it are internal forces, forces involved in those collisions, and that if that's all that's involved, we know that that total momentum of the system isn't going to change. So all of the hard stuff, complications we had with dealing with these really large sort of short time forces that are involved in collisions, all that kind of goes away. We can just look at this initial momentum at the start of the situation and the final momentum, and we know that they're going to be the same, right? So we can look at, problems that involve multiple objects that, bump into each other or push off each other or anything like that, and very quickly, and we can see how useful this is. So, what canonical example you'll see is something like this, where you have, railway train cars on a railway track, right? We have, just say we have one parked car with some mass m. We'll say they're the same mass, m1 equals m2, and just call it m. And we have one of these carts sliding along the track, hits the second cart, they connect, they stick together, and then they are moving afterwards with some final velocity, right? We just derived that the total momentum at the start is equal to the total momentum at the end. That was sort of our conservation of momentum we just defined or derived. So what's the total momentum at the start? Well, it's just, the momentum of each individual cart. So we have M1 V1 initial plus M2 V2 initial. And we know that that's going to be equal to M1 V1 final plus M2 V2 final, right? Um, V2 isn't moving at the start, so we know this is 0. So we end up with just M1 is times V1 initial is equal to M1, the total momentum at the end, M1 V1 final plus M2 V2 final. But if they're stuck together, like they are in this case, where they've stuck together, they both have the same final velocity. So I can just factor out M1 plus M2 and factor out that final velocity like that. And I can very quickly say, well, my final velocity is just going to be equal to mass 1 times m1 plus m2, or divided by m1 times m2, times whatever that initial velocity of the first part was. And very quickly, uh, I've derived, the final velocity here. I haven't had to do anything complicated with, you know, non-constant forces or anything like that. In essentially 1 or 2 lines of algebra, I've figured out what the final velocity of this situation is. So you can see it gets very useful. A side note, collisions like this, where the objects stick together at the end, we refer to as perfectly inelastic collisions. So perfectly inelastic collisions. And we'll get into why they get that name in a few lectures and a few videos from now. But just know it's a very common type of collision. If you take a clay ball and throw it at something and the clay ball sticks to it, that's a perfectly inelastic collision. These sort of train cars that stick together and clamp together are perfectly inelastic. If you were to say shoot a bullet at a block of wood and that wood the bullet sticks into the wood, that's a perfectly elastic collision. Anything where the objects stick together after the collision, which is a really common situation we're going to see. All right. The last thing I want to mention about all this is we've been doing this in one dimension, more or less, for simplicity because we're getting new to it. The same thing happens in 2 dimensions. Not much of what we actually did in that whole discussion and derivation really changes if we consider the vector nature in multiple dimensions, right? So what you end up with, we sort of showed that P initial for the system is going to be equal to P final for the system. That's still true if we're in 2 dimensions or 3 dimensions. The only thing that changes, nothing changes. We just have to do this component wise. So what we end up with is a conservation of momentum where the total initial momentum is equal to the total final momentum. But we do that in components. The total momentum in the x direction at the start is equal to the total momentum in the x direction at the end, and likewise in the y direction. So again, what we've spent today doing is sort of introducing this concept of momentum and impulse, and showing that for collisions and systems of objects where all the forces are sort of internal and those Newton's third law action-reaction pairs, we know that the total momentum of that system is conserved. We've derived sort of a new conservation law for us that can be really useful for handling situations that would otherwise be very difficult to deal with. We're going to go through more examples in upcoming videos and in our synchronous sessions. So if you have any questions, email me and we'll get through them.